Okay, my friends, this is going to be really interesting. This is a guy called Myron Cook, and he's apparently a geologist. And he just put this up 9 days ago. And he's discovered the origin of a beautiful rock formation. And I'm just going to play it for a second. Don't forget, Fair Use Act. I'm sure I'm going to have something to say about its origin, and it won't be what he's going to say if he's following mainstream. Let's see what he has to say. Here goes.
Internet world, I hope your day's going well. Mine sure is, because I'm out doing geology, which is my favorite thing to do. Now, one of the things I love about hiking around, just looking at rocks, is you hike into areas that most people don't hike to, and you stumble across very interesting things. Let's hike right over and take a look, okay? This amazing.
All right, I'm going to stop right here. Now, I'm going to just comment on things that he's pointing out and see if what makes sense and what the geology is, what the chemistry is here. This formation, well, I'm going to let him speak, and then I will speak to what he has to say.
Amazing and beautiful layer dips steeply at about 45 degrees and...
All right, let's look at this carefully. What specifically are we looking at here? Look at all that down there. This is protruding from the wall. All right, can you see that? It's protruding from that wall. All right, let's back it up a little bit and look at it again as he scans over it. You can see it. See it protruding from the wall, and
this amazing and beautiful layer dips steeply at about 45 degrees.
You see the different color? That's fleshy, and whatever this is now protruding from this fleshy area. The other ones are just protruding. Well, here now, down here, you see some more fleshy area, but that one is definitely good, and this one is.
Has eroded into a classic series of shapes that we call flat irons.
Now, they call them flat irons. I don't know, obviously there must be a lot of these around, or I don't know. I never really paid any attention to this, but here goes.
I'd like to show you where this neat layer of rock is in the rock record. So here's a stratigraphic column that shows that rock record from the oldest to the youngest, and with the ages named here.
All right, I'm going to tell you right now, this is biology. All of this stuff is trying to account for all the layers of tissue. And every layer of tissue is separated by like these balls and stuff. You see them? They even show them in here, which are the tendon balls. They even show them. You see it? All of that is tissue layers. Let me just show you something that will illuminate what I'm talking about. Because he shows his, I'm going to show you mine. All right, he showed his, this is mine. Now, he's showing the exact same things, and he's even showing where the tendon balls are and stuff too, which are in, there's a lot of interstitium. Interstitium is a bunch of balls that lays in a web that allows you to flex and these things to move and all that. Now, this was one creature's body tissue in just one little area of his body. That is muscle right there, and this is connective tissue. This was a very strappy area. This is very heavy-duty connective tissue. This is muscle. More muscle down here. This, it appears to me, that would be where literally skin and the hide or whatever scales on the outside, and then it goes right into a ton, and I mean a ton of layers. This is not sedimentation. This is biology. Now, this one little section didn't get destroyed. I don't know why, but this is what I say happened, and not in millions of years, in a click of a second. The guy fell over dead. Okay, and again, Fair Use Act, I'm not trying to steal anything. I have transformative comments. Now, this is nothing more than just what I just showed you, layers of tissue. And this is actually an interstitium layer. And this is the layer, apparently, that he's talking about, this frontier layer. Now, you can see, look, muddy, shell creek, these different colors mean there's different layers of interstitium, of membranes. I'm telling you, that's what it is. Okay, he's got a map here that apparently represents what was there at the time these formations were formed. And he's going to try to explain how these formations came to be. Don't forget Myron Cook. And so I'll let him speak.
This frontier time. And it was here, probably just offshore, is where this special unit was deposited. Let's go.
All right, these are the flat irons again. Now, this is what I want to see. What's the difference in chemistry between these different layers? This is interesting. Now, we're going to have to look at it closely. But I'm going to let him talk and try to discover some of his work. And I appreciate the work because I'm trying to solve these things too, as he is. But I can tell you right now, that's something, this is all part of this same formation. And it's not just a swale. This is, in my mind. Anyway, let's see.
Let's go down there and take a closer look. Is this surprising you here? I know when I first saw it years ago, it kind of surprised me. Let me show you something about this. Get my rock hammer. Look how deep I can go into here. This is soft, soft stuff. And this soft material has got that popcorn feel to it. And look, I wanted to show this to you, if I can get it to focus here for us. Okay, and it can break up. I can break it up pretty easily. Really interesting material, isn't it? It's like, well, if it's so soft, why is it holding up? Why is it making these flat irons that we saw in the drone video? To have flat irons like this, to have this rock going up and staying up in the sky, so to speak, you need really hard rock like a limestone or a well-cemented sandstone. And here, it's soft. So I've jumped up over here on the other side of the valley, kind of the ridges, you can see them behind me, to show you this principle of what we would expect for hard stuff. You know, for hard things. That's what stands up on a ridge. This is a miniature version, not very big.
Now, look at what you're seeing. These, as you know, there were dragons on the earth. Now, all of these things, dragons had like little vertebrates on them. I think this is where the vertebra attached and it's eroded away, and this, you know, everything's made of clay. We're all made of clays, and I'm going to go through the way the different clays are, and there's different clays are in different areas. Now, I don't know why the center of these would be that kind of material. It would erode to that. This I don't know. Although I don't know what this is, what kind of chemistry this is, but I can tell you one thing. This certainly looks like whatever it was here and formed huge. Now, I don't know, is there anything over on that side? I don't know. You know, I can't help myself. These are the kind of things I see as a challenge. I am just going to ramble because that's all I can do. I don't know. But I'm going to tell you one thing. This is not the same as this. And this appears to be part of this, or is, I'd have to really study the abrupt transitions of what exactly happens between this and that and this and that and here and the bottom of the cliffs, and there's going to be transitions. There's no question in my mind that this is all part of the same creature. No question whatsoever. What it was, I don't know. All right, I really appreciate Myron Cook's work here. This is so important to really dig deep, and this on-site stuff is fabulous. And Myron, I appreciate it, my friend. Thank you.
That's what stands out. The soft shale that was on top of this, I can look down here, it's stripped back. It just strips right clean back. So I want to show you how shales normally erode. See, I'm standing on soft shale right here. This is soft shale. It's a dark colored shale, and it erodes into a valley. It's because it's so easily eroded, it's the place that erodes the lowest. So it makes these beautiful valleys like this, and it happens at a small scale as well. But yet, when we look at these tall flat irons, like we call them, this ridge, we don't see that.
I see a creature. Now, I see this, and you can actually see these little things here. Now, did it lie on one side? And this is coming over this way? I can tell you one thing, as far as I'm concerned, that's no question whatsoever. The two of these were at one time a creature that was growing together here. And it looks to be a serpent-style creature with all these little segments, because that's how the damn things move. All right, they're not scales, I don't think. I can't match that, but I think this is exactly what it is. I think that ridge is this, and those flat irons are these little ribs that have eroded away, and the flesh, it is upside down. You'd have to go upside down, and these are coming up that swale, and the other ones are probably buried in the ground, perhaps. I don't know, but that's the only thing I can assume looking at those things. There's just a ton of them, and they keep going down. I don't know how far they go, but it's quite a ways. Okay, so here we are back again. I'm going to let them continue. But what I think this is the backbone, and it was died like in this posture. And this came over here, and the ones that were coming up over the top just eroded away. And these are whatever those bones were made of that are so extremely flexible, because they're not the same as a normal bone. I don't think they have extreme flexibility in these reptiles. All right, this is Tyson's Mud Fossil Adventures, Tyson Carlson. Now, he is out on site looking at this stuff here. Now, you'd think, well, maybe that's ribs. It's way too small of what should be here to be ribs. These are like fibers of tendons, something like that. Where do you see the size of the thing that we're talking about here? So he's just looking around, he's scoping around. All right, you see this all over here? You see this borderline here? Now watch. There was all these tendon balls are in here. That's interstitium. In us, you need a very, very fine microscope to see those. And that's just one very thin layer of tendon is right here. These are balls. You can't, he shows some of them are still really perfect. But this is how thick this interstitium layer is. And it is that thick. Now, he's talking about this being, watch this, let him talk, here it goes. You see this stuff? Here's where the balls were, see?
Okay, we got...
Now look, this is one layer of membrane. This is another layer of membrane. This is a whole nother layer down till you get below. And they're all different materials between the layers. That's why they have to be separated in membranes. So he's going to find, here goes.
Have more biological here. Look how this just wraps around and curves, and then it comes in.
Now look at this. Look at this. This is the lower layer of a membrane. This is an upper layer of this same membrane. I think it's about maybe 6 feet up, something like that. Now he's going to come in and focus in on a couple little spots.
Into this. This is so cool.
Look at this. They have fireplaces in.
And then into this.
Look at this.
Oh yeah, Geology. Isn't this cool? Oh, this is just lava.
All right, you see this here? This little area is, well, I'm going to show you the biological, but that's, you know, and that's how they explain it. Oh, this is just lava flow.
No, this ain't lava. This ain't even the same material as lava. This is more sandstone-y.
See, they put fire pits in there.
Something was sitting in there.
Now look up there. These are different layers. They're all different layers of membrane. This is just amazing. Where did I show you what they really look like anatomically? Don't forget, this is what we're talking about, is this interstitium with this layer up over the top of it, all the little black balls that are wedged in that fleshy layer. And then when they erode, this is what happens to them, just like down below here. You see them? They're all over. And this is mud. Mud is clay. Clay is from eroding skin and flesh. All right? These balls are a whole different story. They're made of a very, very tough stuff. And they're tiny in the skin and area, and they're big in other areas. And because the creature's so huge here, they're just gigantic. Some of them are the size of houses. I'm serious. It's unbelievable. They're all over the earth. And here's what they look like inside of you and me. You see this? You can't even see them here. They're so small. They focus way down into them. You can see this. And when you get way down into this fabric like this over here, that's what they look like. All right. Every creature has all of these different layers of tissue. You start with the mud. That's your skin and your fleshy stuff. And then you get a little bit of calcareous stuff. There's a little bit of grittiness, and then a little more grittiness, and then some stony little, those little tendon balls will be in here, and then it gets worse, and then it gets more into organs and so forth. And then you end up at the top, calcium carbonates, which is your limestones. But they still have slightly argillaceous. All right, there's argillaceous, then there's slightly argillaceous, then there's just raw limestone. Well, what's this slightly argillaceous mean? All right, it's all about clay. Clay is the skin and the mud that erodes from creatures' bodies. So now let's go over this one more time, because slightly argillaceous, the argillaceous part, the clay, the slippery stuff, is what coats the tendons so that they can move back and forth against themselves. It's a slippery coating. I call it, I can't remember what I call it. I'll think about it in a minute. But you got argillaceous, which has got a lot of slipperiness to it, really slimy. And then you got slightly argillaceous, and then you got none in some limestone. This is in your Achilles tendons and stuff like that. Well, not actually. They're slightly argillaceous. This must have washed out all the clays from this. So the limestone is really tendons, but all of the clays have been washed out, because limestone doesn't wash out easily. Now let me show you something about Devil's Tower. I tell you, all these things are giant creatures. Devil's Tower was a foot. I'm going to show you about tendons, and I'm going to show you what slightly argillaceous means, coating limestone. All right, you've seen all my mud things, mud fossils, and then you've seen my lungs, and this would be somewhere right up in here somewhere, Caesar. He'd be all those things. It just means you get less and less refined. Mud is just mud. All right, so anyway, let's see what argillaceous means as far as Devil's Tower goes. First of all, there's something going around on the internet. Somebody attached this picture to underneath Devil's Towers. Oh, we found all this root system. It's baby corn roots. All right, everybody knows what Devil's Tower is. These are literally tendons. Where you see the red coming, there was a little bit of blood coming up through that area. There's an artery there. This wrinkle zone at the top is because tendons are under tension. When you cut them, bing, they make a wrinkle zone. Some of them have like a wave pattern, but that's always going to be wrinkled back. Now, on top of this, we have that argillaceous stuff. And what is that? It's a slippery thing. So these tendon fibers can move, and when you move all these different directions, they slide against each other. And I'm telling you something, it's a synovial sheath is what I was trying to remember before. Listen to this. I'm going to see if you can see this, because I don't want you missing a thing. I don't want you to miss a thing. Look at this now. We're looking at coefficients of friction. Well, what does that mean? How hard something scrubs against something else, how much friction there is. Well, how much friction is in Teflon against Teflon, ice against ice? Very little friction. If you can see these numbers, and I am having a hard time, Teflon on Teflon, you got two different ways. Static is where you're not really pulling at it, and then kinetic is where you're really pulling at it. Now, Teflon on Teflon is 0.04, and it stays 0.04. So it doesn't get any better, it doesn't get any worse. Listen to the synovial sheath. It's 4 times slipperier when it's not having any static. And when you pull it, look at this. It goes from 4 times slipperier up to 0.003 instead of 0.01. It goes exponentially more slippery. That's why I've discovered that in the morning when I get up, I just sort of barely tug on my back muscles, rocking my knees up and holding my knees up. Just, never hurt, no pain. Just gently rocking them up, and it just stretches all that out. Because what you're trying to do is stretch out and get that fluid. Now, I work with a physicist, anatomist, and he does autopsies all the time. And he says he can tell when a guy is in pain and his muscles are stiff and his back is bad and everything just by the fascia, which is this synovial sheath stuff, this what is coating these fibers. I'm going to show you what coats them. And he says if he normally can just go like this and it all just sort of splishes away, and he knows that guy's nice, he can move it, no problems. He says other guys, he has to cut them with a scalpel to get that stuff out of the way. It's so fibrous and tight. Now, let's see if we can see these actual slippery coatings around these fibers at Devil's Tower, and we can. All right, this is Devil's Tower. I just want you to see something. I don't know if you can see that or not. But synovial joints, which is the stuff that I'm talking about, the slippery stuff. Look at how slippery it is compared to other things. You can look at that later and make your own determination. It's the slipperiest thing there is. There's nothing slipperier than synovial fluids. And look, under tension, under a kinetic pull, they get almost unbelievably, there's no tension at all to them. That's why these fibers can slide up and down on themselves. And that's why they're always under tension. And you can move this way, that way. They have to be able to and they're always going to move a little bit when you're twisting, a little bit this way, a little bit that way. And I have a friend who's an autopsy anatomist, I'm working with him for 10 years. He told me he knows when a person is stiff and can't move by the condition of the fascia. Normally he can move it with his fingers, and he says that person's fine. He says other people he can't even move it. He's got to cut it with his scalpel. He says that he knows that person's continuously in pain, and I know I know how it works, and I know how to fix it too. You just have to barely work at those areas, just not enough to hurt them, just enough to give them just a little bit of stretch, because that's the kinetic portion. It brings it down from 0.01 to 0.003. That's almost no resistance at all. 0.01, you got some resistance. 0.003, you're just sliding around and just having a good time. Now, that's the wrinkle zone from the tendon being under tension, bling, as it snaps there. They all do that. Now, whoops, turned it off by accident. Now, we're going to look at the synovial sheath that surrounds every one of these. As again, you have to be able to move. Otherwise, you're stiff and you can't move. You see that? That's Devil's Tower. This is that synovial sheath that's around each one of those fibers. And that stuff peels off. This guy better be careful. You see it? And this is all wrinkly now. Normally you stretch it out and it'll come and stretch and it wrinkle, unwrinkle, and it'll just be fine. But that's what those fibers are. Look at the size of those things. Just think of the size of these creatures. All right, here's Tyson again. Check this out.
I don't want this video to go too long.
You see, this is really slimy stuff. And wherever you see green growing, that's red blood.
Okay,
Look at
we
this.
gotta get this pattern here. This is
Look at this. You telling me that's just accidental?
biology. Look at this. This here is biology. It's soft too. It's kaolin clay. This is absolute biology. This is so cool. Yeah, we get excited here today. We got a lot. Scott just broke this open. It's more of that clay. Just, you can peel it with...
This goes back several years, I believe. Scott Wiles sent me a picture of something that nobody could explain, and it was a tendon anthesis just sticking straight up, and I knew what it was right away. I said, ooh, ooh, ooh. And I think I did a video on it. And Tyson got a hold of me, and Tyson went out with Scott, and they started discovering this stuff together. Now Scott travels, but I just did hear from him. And I think it was about this particular stuff, this clay. Here goes.
With your finger. Look at this. I can peel this with my finger. Look at that.
Now, where we were looking at that bentonite looking stuff, I don't really know the source of that, but what I think it was is the bones of a giant reptile. That's all I could think. All of those different little vertebrae, it looks to me. This is some more of Tyson's area out there. I believe this is either a heart, I think I would go with a lung. Hard to say, but there's a lot of blood, and these big rocks are another type of blood, the black blood. There's red blood and black blood. Now sometimes it's hard. It's really hard to tell some of this stuff. It's just so huge that it's just amazingly hard to understand, to be perfectly honest. Okay, this is some kind of deep chemistry on rocks, and you got sandstone, mudstone, limestone. Well, look at this. You see this right here? All of them. What is that? It's iron. They all have the same amount of iron, basically. The same type of iron in them, because we're living creatures. And they also have a lot of silicon and, all the same stuff we have in them, the transition metals that I talk about. Now, let's look at a whole layout of them. I'm just going to flash this. If you're really that deep into it, you can come back and look at it. But it talks about kaolin, plastic case, feldspar, talc. Now, I have little samples of each of these things here. Diatomaceous earth, bentonite, kaolin clays. Kaolin comes in skin colors because it is from skin. All of these are different layers of tissue, and some of them are very fine, which is the fine clay they make in the real fine china clay, and which is made from kaolin. And then you get into other clays that have more minerals in them. Now, I got interrupted a couple times, so I may have shown you this, but let's go back through it again one more time. Clay is at the bottom. This is where you start with the mudstone, which is nothing more than that kaolin clay. And then you get into a little bit gritty, and then you get into the really gnarly stuff, and then it ends up being limestone at the top. But this is that slippery stuff I showed you on the tendon fibers. And the top ends up being calcium carbonates, and that's washed out limestone. That's really tough stuff, hard. All right, he's going to be talking about this bentonite clay, this montmorillonite clay, and how many layers of layers there is. Now they claim it's from fossil things. Well, I disagree with that. I believe it's from creatures' bodies, which are fossil things, but here he's going to talk about it now. They use that to clarify wine, actually. Here he goes.
They actually call this clay the clay of 1,000 uses. So how is it that this montmorillonite clay, or this bentonite, absorbs so much water? What is it that actually happens? Well, I want to show you a sketch. I'm not a crystallographer or a geochemist, so it'll be fairly simple.
All right, it is very simple. I'll let him explain it, but when I show you layers of tissues and things, it's unbelievable how many layers there are. And when he tells you the thickness of these layers that are in these clays, you're going to have a hard time believing it, but it's true.
And that's probably good, isn't it? I want to show you the structure of the clay. They're sheets, super thin sheets. This black here, that's a sheet, and one here, thin like mica, 1 nanometer thick, each of these. Well, a nanometer, that's 1 page. If you hold the page on its edge and look at the edge of that thickness of that paper, that's about 75,000 nanometers. And this is one of those. Gives you a feel, okay? So they have these sheets, nanometer thick sheets, and there's a space there where it has sodium in this case. There are 2 types of bentonite. Calcium cation that can be in here, atoms of calcium, or sodium with a positive charge, cation, either sodium or calcium. Sodium's the best one. Turns out Wyoming has 75%, 70% of the supply of sodium-rich bentonite. Whew. This is the beauty. Okay, so there we go. We have.
All right, I got to tell you what. You should watch this if you want to get into the deep chemistry. But I'm going to bring you to the point of trying to understand what he's looking at there. Now that we have a good feel for the particles, and they are absorbent. Now, I am going to tell you right now, I think it's the skin, the bones, literally the bones of a snake, which was a reptile back then, whatever it was. In the reptile bones, I believe they are a little bit different than like a human bone or that type of thing. They are more flexible, and I believe they have more collagens in them. And that's why it's just all fluffy like that. He can just crunch it up. But I do believe those are bones that have decaying now. And because of this sodium bentonite, sodium causes things to sort of disassociate and break down. So that's why sodium bentonite is so broken up into little popcorn pieces. Okay, he's really, I can't say anything bad. All I can say is that now he's going to go into the mainstream discussion of how this all happened. I'm seeing this as biology, and I think it is biology, but anyway.
You can get into this a bit. Well, I've told you this is montmorillonite and the amazing properties it has. Now the obvious question is, well, how did it form? What is it? And it turns out it is altered volcanic ash, primarily volcanic glass. Altered volcanic ash? Are you kidding me? That's That's 10 feet thick. If you measure the thickness of it,
Okay, I'm not going to drag this, and I don't want to be disrespectful, but to allow yourself to think that these formations just form from some kind of volcanic ash, that's a stretch for me. Okay, like I say, these are, as far as I'm concerned, those are snake bones. And they have a little more flexibility, and because of the sodium, the extent of the sodium in this area, you would get that kind of breakdown, I believe. Okay, I want you to pay attention to this. I think this has something to do with the skeleton coming up and the head is up in this area, but that's as much as I could see of that. And he's coming around.
this amazing and beautiful.
You see this? This is different than down here. Something happened in his neck and his head or something is changed. This goes all the way down around and it gets smaller and smaller as it goes down. That's just the way snakes work. Now, this is the one,
Dips.
you see this? Something's going on with that. And something's going on with this. Totally different than what's going on, well, not totally different, but a lot of difference. Now,
Deeply at about.
you see this one right here? This is where I can see the flesh attachment. All right, come around.
45 degrees.
You see this right here? That's the flesh attachment.
And has a.
Let me back it up here and just do it again. Here we come around, and you know, like I say, this whole area here, I believe, was the backbone, and the ribs came over and went right in like this. And they, of course, would be coated with some flesh, which all that's eroded and run down this gut line, basically. And that is some fleshy area, and that's the only, well, it's not the only one, but it's the best one. So he's looking over here.
And beautiful layer dipped.
Whatever that is, I don't know, but that right there is some pretty serious flesh.
Steeply at about 45
See it?
degrees.
That's the flesh.
And has eroded into a
Now, there's flesh on every one of them, basically, and that's where they go down, and they all dive in the same way. And see them all the way down? See, that's not volcanic eruptions. I'm sorry. I mean, this guy's a nice guy, but to think that would be very hard for me to understand how he could come to that conclusion.